Alright, time to get your robots moving. To give you a bit of preview of what you should expect from your robots, I have a little interactive widget here on the course website for this chapter. If you push play and don't have patience like me, you can scroll faster. You'll see that I'm sort of expecting all of your robots to veer off course. If I run this a few times, you'll see it veers off course in different directions each time I run it. Instead of telling you why it veers off course, I'd like you all to think about it, and if you'd like some of my comments on why your robots are expected to veer off course, you can click this little tip button here underneath the interactive widget. So that's the goal. Get your robot to move vaguely forward, and we'll take some measurements and just see how wildly far off forward your devices go. I occasionally make changes to our class code. So it's always good to start being in the code repository with a git pull. So it looks like mine is up to date. I'm not giving you all the code that I write each chapter. The goal is for you to see how I would do it and then for you to code it on your own. You'll get a lot more out of it if you have to struggle with the syntax and try to make your own version of whatever I write here in the videos. So my previous demos are here in untracked demos, and I think I'll start by making a new directory, and I'll call it go to goal open. And that'll be different from what we'll do next week or the week after, where we have go to goal closed, which should get us right on target instead of relying on what's called dead reckoning, something I'll mention again in this video. So inside go to goal open, I'll copy from last week's demo the package.yaml file. We're going to use some of the same dependencies that we had last time. I think I'll also copy the tweet file. So this is the file we're working with. And the big difference is now we're going to be controlling the motors from this file as well. So we'll need to import motors. And if you dug around with the motor script last week, you'll know that we'll need to create a motor object. I'm going to group these slightly differently. And one thing I've noticed while coding in Toit is I get a lot better auto completion if I manually specify the types here. The first important thing to do is whenever we start our program, we want to make sure that our motors are in the halted state. They're not actually moving. That being said, you might notice while programming your microcontrollers the motors move. That has to deal with the fact that some of the pins on the board are used for multiple purposes, and they might be used for something during the programming process that your motor drivers will interpret as asking the motors to move. And if it makes sense for us to stop the motors whenever we construct it, it also makes sense to stop the motors whenever we have disabled the device, meaning we've lost connection with whatever's controlling this externally, for example, the web page or using WSCat. Since all we've done so far is add the motors and stop them, we're at a point here where it's probably worth running the code and making sure it works. I'll start by plugging in my microcontroller. And pretty soon we'll see how to do this without plugging in your microcontroller at all. But for now, I'll start with Jag Monitor. Looks like I'm lucky enough to get this to connect pretty quickly. And over here, I'll open up a second terminal, and we will move into the go to goal directory and call jag run. And actually, that reminds me, it's probably worth setting the IP address. Do I have the same IP address that I had last time? 172.286.208. It looks like I do. So let's upload this program. And remember, when we call jag run, it uploads it into RAM, meaning every time you restart your device, you'll have to re-upload that code. All right, I'm getting the errors, and these errors are because I haven't installed the dependencies, but that's why I've copied over the package.yaml file. So I should run jag package install. When you run jag run and there are no errors, that means the program is valid and it was able to upload it onto the device over Wi-Fi. So jag run runs over Wi-Fi, and then jag monitor, the connection over here, is running over the serial cable. So that's a physical connection, not wireless. Okay, so my program's running, and it looks like I could connect to the IP address listed here. But before I do that, you might notice that my display here is inverted from what I might like to do, how I might like to read it. In an update to the display library, I added the ability to invert the screen. And so the new constructor here has a default of false, so if the orientation was fine for you before, it should remain fine. And then that just gets passed on to me calling the pixel display. So let's see what happens when I add inverted equals true, and then rerun jag run. I now have my display in a better orientation for recording and reading it from where I'm sitting. Next, we should check if the basic LED functionality still works. We haven't broken anything. So for that, I'm going to use WS Connect. And I will this time use my variable jag IP. But I still need to manually specify the port number listed here at the end. And I'm not going to assign that to a variable because that will change frequently. Even as I just re-upload different versions of the same program with jag run, that IP address will be incremented. Alright, we have a connection, and I noticed that the LED light did come on. I'll send a packet, and it comes on again. So it's enabling and disabling just like we'd like. One last thing to check is I'm not actually powering the motors here. Let's see what happens if I run my same program with the motors enabled. The LED lights up, the motors don't do anything, which is exactly what we'd hoped would happen. If I look at where I'm using motors, I'm only ever calling motors.stop. At no point in time am I actually turning them on. Let's see what happens if we turn them on. One way to do that would be at the bottom of enable to call motors.setSpeedForward, and let's just turn them on a little bit. Since I've changed the program, I'll need to re-upload it. One thing I should note is it's always good to turn off the switch when programming. The only reason that motor was moving was because during the programming process, the pins that are connected to the motor driver are getting sort of spurious information then telling the wheel to move. Now if I flip that on again, the motors shouldn't be moving. But if I connect, and here's why I didn't have a variable for the port number. It's incremented to 59045. When I send this packet, the light should come on for a second, and the motor should move for 1 second. And they should each time I send a packet. And as long as I keep sending data, they should remain on. My goal for you all in this exercise is to do this in a little bit more sensible way. I don't want you manually controlling the robot and having it go a specific distance. Instead, I want you to figure out how fast your robot goes at different speeds. So I'll remove that from here, and instead what we want to do is something to this effect. I want to do something if the LED blinker is enabled. I'm just putting this print statement here so that the indentation is correct, and in case I did want to send something over, it'll work. But before I do that, I no longer really like this name, LED blinker. I'm going to change that to, let's say, the forward mover. And likewise, the name of the class should be something similar. So let's call that the forward mover class. You can see I changed it in both places. So if we're in an enabled state, we want this thing to move forward. So let's say forward mover, grab out the motors object, call set speed forward, and let's put it at 50% speed. And I should really say that's actually 50% PWM, or 50% duty cycle. It's not actually a one-to-one mapping to the actual speed we get. The only way we'll have that is if you do some precise measurements, figure out, okay, when I do 0.5, how fast does it go? When I do 0.4, how fast does it go? And essentially doing like a regression over that data. Or better yet, instead of using open loop control, which is what we're doing here, you would use feedback control. That's not something we'll discuss for this exercise, but it'll be coming up very soon. For this exercise, it's enough to try to just get close enough to the target zone. So I know I have my motor set to about half speed. The question I don't know the answer to is how long do I need them running at about half speed? And that's where I'll add another variable here. And let's say it's 5 seconds. I think that's a little bit more readable way to write 5,000 versus something like, especially when I start having something like 50 seconds or 500 seconds. Easier to interpret when you have the underscores in. So this will have my robot move forward at half speed for, in this case, 5 seconds. And then I can brake. One thing to note is that this isn't a guarantee. The motors actually might stop in the middle of this, and that's because this disable function is called from WS communication in a separate thread of execution, a separate fiber. So really, we're just checking here that we don't start until it's enabled, but there's no guarantee that we'll actually move forward for a move forward amount of time, and I can demonstrate that. What should we do if the robot is not enabled? Well, I'll just propose that in this case, we also sleep, and maybe every 1 second we check to see if the robot's been enabled. There's no reason we have to delay it 1 second here or any amount of time. I could just leave off the else and it'll work perfectly fine. And so I don't forget, one thing I should mention is that I'll want you to run forward and try to hit a target about 10 times. And this code will only run once. So you'd have to re-upload it, and by that I mean it'll only move forward once. You'd have to re-upload it every time you wanted to move forward again. So if I were all of you, I would add an external loop that takes this code and runs this multiple times depending on certain conditions. For now, this code is actually enough to complete the exercise. So let's see what happens when we program our device. And again, each time I program, I should really flip the switch. I should really turn off this switch. I should really turn off the switch anytime I'm not powering the motors themselves. So I've uploaded the new program. I'll turn on the switch, and we'll send a command to enable. And in this case, the IP address is 46. The motors turn for just 1 second, even though I asked them to do 5 seconds, because they were disabled by the communication module. Even if I were to run this again, they're no longer going to be enabled, because I only call forward once here. So in this loop, I could create a loop here that repeatedly checks to see if it's re-enabled. But I think a better option is just to use the web form, which continually sends heartbeats, or if you're lazy like I'm about to do, re-upload the program. I will remember to turn the motors off at some point. And whenever you connect, changing the IP address, just continually send packets so that the disable function is never called. And you might see one problem with my code as it currently stands. I've definitely been doing this for more than 5 seconds. And the problem is, after I move forward, I forgot the command to stop the motors. Let's do one last demo to show that this now works the way we intend. And again, I really encourage you to find a better way than to re-upload the program every time you need to make it, to restart it. It'll get tedious to do that. And I forgot to turn on the motors, so that's another false start. Too lazy to turn it off this time. Different IP address. I didn't get it in time. Let's hope this last time's the charm. And the motor stopped.